Okay, so now let's do some logistic regression analysis on Python. So we're going to import a really nice data set that is the iris data set. So let's first of all look at the keys of this data set. We've got the data X, the target Y, target names, and so on. Let's take a look at the description. So iris dot description, and there you go. So this is a really famous data set that contains the sepal and petal length and width of 150 iris flowers of 3 different species. You've got the iris setosa, the iris versicolor, and the iris virginica. Okay, so now using this beautiful data set, let's try to build a classifier to detect the iris virginica type based only on the petal width feature. So first, we've got the data over here. So let's extract the petal width. And to do that, well, let's take a look at iris data. And as you can see, you've got 4 columns. So we go back here, we've got those 4 descriptions. So we've got sepal length, sepal width, petal length, and petal width. Now, since I'm interested in the petal width, I'll only extract the last column, right? As such. And now, we'll insert it in a vector X, and the target values are extracted as target. So they're either, so for the moment, if you extract them as such, you get either classes 0, 1, or 2 that are iris setosa, versicolor, and virginica. So since we're interested in classification, I want to classify virginica. So as such, we get a true or false, true for virginica, and false else. And I want to cast it as type int. Oh, I forgot brackets over here. There you go. So either 0 or 1, and store them in a vector called y. Okay? Now let's train using logistic regression. So for that, I'll go to linear model. I'll import logistic regression. And I'll instantiate logistic regression. And then I'll fit y versus x. There you go. Now let's take a look at the model's estimated probabilities for flowers, with petal width varying from 0 to 3 centimeters. So for that, let's take NP line space. From 0 to 3, I choose 1,000 points, then reshape as such. Oh, this is X new. Okay, and now let's predict the probabilities of X new using this model, right? There you go. And now let's plot X new This is Y proba in green and label it as Iris virginica. Now let me plot this, and there you go. Okay, looks good. Now let me also plot x new y proba 0 that are not virginica, right? So I'll copy paste this and just type just before it not virginica, and there you go. So let's insert a legend over here. Okay. So let's talk about this plot a bit. We really have nice interpretations here. Now you can see that the petal width of Iris virginica flowers, represented in triangles, range from 1.4, something like 1.4, right, till 2.5, right? While other iris flowers in square generally have a smaller petal width. That is, it ranges between 0.1, ranges from 0.1 till 1.8, right? Now notice that there is a bit of a overlap, like this region over here. We've got overlapping. And this is where it gets really tough for the classifier, right? As you can see, above about 2 centimeters, the classifier is highly confident that the flower is an Iris virginica, right? Because this probability more than at 2 centimeters, we've got a 0.75 probability that this is an Iris virginica. While below 1 centimeters, that is here, we're sure that 0.16 of the time that this is a virginica flower, and 0.83 of the time this is a non-virginica flower, right? In between these extremes, so between 1 and 2, right, the classifier is somewhat unsure. However, if you ask it to predict the class using the predict, let's say we go down here, log regression dot predict, let's say 1.7, it says it's a 1, that is, it's an Iris flower. It's a virginica flower. So at 1.7, right here, we're 0.58 sure. Well, how about if I pass it 1.5? It tells me it's a 0. So 1.5 is less than, it has a probability 0.43, which is less than 0.5. Hence, it's classified as a non-Iris virginica. Okay? Therefore, one really important thing to keep in mind here is the so-called decision boundary. So what threshold right here should I, classify virginica versus non-virginica? And the answer here is about 1.6. It's the intersection of both functions, right? And we can see that at 1.6, the probability is 0.5. So we come at an equilibrium here, right? If the petal width is higher than 1.6, we say that the classifier will predict that this given flower is an Iris virginica. Or else, if it's lower than 1.6, it will predict that it is not, even if it is not very confident. And actually the way you can get your decision region is by simply typing down decision boundary. So it tells you that this line over here, it's at 1.61, right? Now note that here we use this logistic regression to train on one feature. That is the petal width. Now I'm going to copy paste this right here, and I'm going to work out with both the petal length and width. So doing this, then I'll copy paste the regression code because it's basically the same. So right down here, go. And now that we trained our logistic regression model with two features, the petal length and width, I'm going to open a mesh grid because we have two features. This could be accomplished using NP NumPy's mesh grid as such. So for the x-axis, for the x0, so for the first feature, I'll do a line space going from, let's say, 3 till 7 with 500 points, right? I'll reshape according to such. For the and for the second feature, I'll go from 0.8 till 2.7. Okay, good. Now let's take an x new vector that is composed from x0 and x1, right? And now for the probabilities, I'm going to predict using x new. Using x new, right? Now I'll open a figure. First plot the ones belonging to class 0, that is not Virginica. Okay, so here are the data points that correspond to non-Virginica, right? And right here, I'll plot the ones, actually I'll copy paste this because I only need to set the y to 1, right? So there you go. And I'll plot them in green triangles. There you have it. You have a bit of overlap over here. Let's go ahead and get the y probabilities and reshape them before anything. So shape as such. And then now we need a contour. So the contour is going to consist of the mesh grid points. And I'll put a color map as such. Okay? Now, all I have to do is take left, right, NP array, let's say from the limits, and the boundary according to the equation, ax equal b, right? So ax equal b. You can do this using the log regression coefficients. So you'll take the first one and multiply it by LR plus the intercept as such divided by coefficients. Okay, we need to plot it now. So I'll first set a C label to plot the contour, and then I'll plot the left, right, boundary, with dashed black and a line with, let's say, 3, right? So we're going to place some text. So let's see how it looks like at the moment. Very messy. So let's see how it looks at the moment. Very messy. So now let's insert some text because, you know, we need to be able to separate. We need to be able to read the decision regions properly. So for that, we'll go here, insert text. Say down here somewhere, I need to say that this is not Virginica. So say at 3.5, 1.5, not Virginica, right? Set a font size of 14, color to blue, and I will center the text. Oops. So as such, and the same thing for Virginica, but this time in green, right? And we'll change the text, obviously, and the position. So this time, place it on the top right. Say, so it's not showing because, so it's over here, okay? Right, so now let me limit the X and Y axes. So the axes are limited by the mesh grid. Okay, looks better. Good. And now let's give a label. So the X label is petal length. So font size of 15, and the Y label, just copy paste this. It's the petal width. And there you go. Looks good, right? Okay. Now, what we can see from here is that this logistic regression with 2 features can estimate the probability that a new flower is actually an iris Virginica or not. But this is done this time using 2 features, the petal length and width. As you can see, the dashed line over here again represents the points where the model estimates a 50% probability. Just as the decision boundary over here is the point where probabilities are equal to 0.5, well, it's the same thing over here. At this dashed region, we have probabilities equal to 0.5, right? Less, it's non-Virginica. When you're at a point that is lower than this boundary, it's non-Virginica. It's classified as non-Virginica using this model. And on top of this line, it's classified as Virginica. Note that this is a linear boundary in a sense that the set of points are nothing other than a linear combination, so it's a sum of theta I xi, right? And each parallel line to this linear boundary represents points where the model outputs a specific probability. So if I come here and cut on a line, right, and over here, and in 3 dimensions, if I cut using hyperplanes, then all these points that, for example, lie on this purple line have probabilities that are the same. For example, on this purple line, I've got probabilities of 0.15. On the green line, probabilities 0.9. As you can see, a bit of variation over here. The probability jumps from 0.5 to 0.9, or from here to here, the probability decays till 0.15, right? So yeah, this is basically it. This is interpretations using 2 features. So you don't have this nice looking logistic, curve. In higher dimensions, you can you're going to have to start interpreting hyperplanes as probabilities, right? Now, a small remark here is that just like the other linear models, logistic regression models can be regularized using L1 or L2 penalties. And Scikit-Learn actually adds an L2 penalty by default. Now, we've got the data over here, and based on the p total length and width, we're going to classify the three classes. So let's call SoftMax Regression, and this could be done using actually logistic regression, right? Because you're going to set the multi-class to multinomial and the solver, and next you're going to fit y versus x, right? Now, as we did previously with logistic regression, I'm going to copy paste this line of code to generate my mesh because I'm working with two features, right? So this time I'll set the grid from 0 till 8 and 0 till 3.5, right? And then I'll perform prediction on this mesh grid using the SoftMax regression, right? And I'll also predict using SoftMax regression. So notice that here I've got the probabilities, and over here I've got actually which class they are. So it looks at the highest probability. So let's take a look at this. Y proba. So if you take a look at the length, actually not the length, the shape. It's 100,000 by 3, 100,000 samples and 3 probabilities. So if I take a look at, let's say, at the first row, right? We can see that the highest probability is this guy over here, right? Which is 0.999, and it dominates the rest. And since this is the case, then if I take a look at predict, it's class 0. If I go one row down, okay, let's go to row 10, row 110, row 1110. I want to find class 1 or 2. That's what I'm looking for. And there you go at row index 666. I found that the second element is maximum. So if I go here, 666, it is class 1, right? So we've got our probabilities and our predicted classes. Now let's open a figure with size 10 by 4 and plot the first subclass for Iris virginica. It corresponds to those that have target value equal to 2, and same thing for target value equal to 1, which are classified as, which are actually Iris versicolor. And last but not least, the setosa for y equals 0. Now from matplotlib, for a really catchy figure, we're going to import listed color map. And for this custom color map, I'm going to have 3 different colors, each per class. And I've picked 3 colors in hexadecimal. I hope you like them. So let's open a contour, plot the mesh grids. Okay, now we need to separate them by first plotting the contour as such, then giving the C label as such, giving X label and Y label as such. Now one more thing is missing here. So going back here, we forgot a very important thing. That is, from the probabilities, I need to plot them, right? So I'll extract them, I'll put them in a vector ZZ1. And for predict, I'll reshape it and I'll put it in a vector called ZZ, right? So now going back down here, oh, let me first execute this, okay. So this is what we have till now, looking good. And now let me plot the contour. That is, plot the contour, passing it x0, x1, zz1, and the C map, right? Next, we'll plot the contour using plot C label. So we're starting to have a nice figure here. And next, we need an X and Y label. So I'll just copy paste it from what I had previously over here, right? Right here. Petal length and petal width. And next, I need a legend, right? So the legend is set over here. We can't see it. There you go. So triangles for Virginica, squares for versicolor, and yellow for, or circles for Setosa, right? Okay. All looking good. Now let me limit the axis, because the axis is really annoying, right? I mean, we've got a lot of space. So 0, 7. Should do the job. This 8 is not that, you know, there's nothing going on over here. So 7, and for the Y, from 0 to 3.5. Okay, better. Now, that's it. This is what we have. So I'll just show. And there you go. So as you can see over here, we have the resulting boundary decision regions, right? Represented by the background colors. So yellow, Setosa, blue, versicolor, and green, Virginica. This figure also shows you the probabilities for the versicolor class, represented by the curved lines right here. So 0.9. For example, you've got the line labeled with 0.45, that is over here, represents the 45% probability boundary, okay? 0.3 right here, 0.15 over here. One thing to notice over here is that the model can predict a class that has an estimated probability below 50%, right? So even if you have a probability below 50%, you can classify. For example, at the point where all decision boundaries meet, that is over here, all classes have an equal probability of 0.33, that is 1 over 3. So thanks for watching. If you found this lecture beneficial, please leave a like on the video, subscribe to the channel, If you have any questions whatsoever, kindly leave a comment down in the comment section below, and I'll make sure I'll get to it as soon as possible. Also consider donating to my Patreon account any amount you wish. Thanks for watching, and I'll see you in future lectures.